Thank you all for coming to the first TAP Colloquium of the semester, and I'm grateful to Professor Rebekah Dawson for joining us today and for having so many meetings over the course of the day. Rebekah got her PhD from Harvard back in 2013, where I was first honored to meet her, and has gone on to be, I think, one of the most awarded theorists in the field. She's received the Annie Jump Cannon Award, the Bach Prize, a Sloan Fellowship, the Urey Prize from the DDA, and also the Warner Prize from the AAS just last year. So I'm sure we will all be excited to hear the exciting things she has to say about planetary system architecture. Since we have a relatively small audience, I think it's fine if people, if you have questions, you can just unmute yourself and ask them. If you prefer, I can also monitor questions in the chat. So if you have a question but don't want to interrupt, I will be keeping an eye there. So feel free to put something in the chat as well. If you are not in the middle of interrupting and asking a question, I ask that you please do mute yourself so that we don't have any feedback. So I'll let you take it away. Thanks again.
Thanks so much, Caitlin. It's great to visit virtually, and I really enjoyed meeting with folks earlier today. So I'm excited to talk to you today about how theory and simulation are helping us understand the physical processes that establish the wide diversity of planetary system architectures. Planetary systems exhibit a surprising diversity from the solar system, which has rocky planets close to the star and gas giants further out, to giant planets like hot Jupiters orbiting extremely close to their host stars, to gas giants at wide separations at tens of AU, to compact multi-planet systems all packed within the orbit of Mercury. More broadly, a planetary systems architecture refers to a combination of the observed orbital properties of the individual planets, relative orbital properties like spacing and coplanarity, and position and morphology of debris belts. So we'll start with the very simple blueprint that we had for our solar systems architecture prior to the discovery of the Kuiper Belt and exoplanets. So in this very simple blueprint, which starts with a spinning cloud of gas and dust, the dust collapses and gas collapse into a disk. And in the outer part of the disk, where there's a lot of ices available and large feeding zones, a rocky core can form while there's still gas around and accrete a gas atmosphere to become a gas giant. After a few million years, the gas disk goes away and rocky planets form closer to the star. So this simple blueprint leads to a system that looks like the solar system. We have rocky planets close to the star, gas giants intermediate, failed debris at the edge. All the planets are on circular orbits, and they're all orbiting in the same plane. But not all planetary systems share this expected architecture. And so we need a new blueprint for the origins of planetary systems that takes us from the formation conditions, how those trigger different physical processes in different planetary systems, and how that leads to the wide diversity of orbits and compositions that we see today. What we have now is not a blueprint. I was going to compare it to a cookbook, but a cookbook wouldn't have a bunch of different recipes for the same thing. So our situation right now is more like allrecipes.com, which as of 2015 had almost 1 million recipes, many for the same thing. For example, for ravioli, there's one recipe that warns you not to be intimidated by the long list of ingredients, and another that has packaged store-bought ravioli as an ingredient. So this is the situation we're in with competing theories, competing ideas, and no real consensus to put everything together into one picture that explains all of what we see. So how do we know how the ravioli gets made and why some systems have ravioli and some have hamburgers? We now know of thousands of exoplanets, and having this big sample gives us both demographics of the population and then great detail in some individual systems, which is quite complementary. So the theme of the talk today is that in our quest to create a blueprint for the origins of planetary systems, individual system architectures where we can see in great detail about one system complement what we're learning from population-wide demographics. I'll start by talking about the origins of close-in giant planets, Jupiters, and down to Neptunes, because these planets are in stark contrast to this expected blueprint, orbiting so very close to their stars. There's several types of theories that people have proposed for the origins of these close-in planets. One possibility is that they form much further from the star, maybe out like where our own Jupiter does, and then get disturbed onto very elliptical orbits that bring them on close passages to the host stars. Getting so close to the star, tides can shrink and circularize their orbit and lead to a close-in giant planet. Another possibility is that during the gas disk stage, the gas disk can move the planet in towards the star, which is called disk migration. Or maybe a giant planet can actually form much closer to the star, despite our original expectations. So a few years ago, we tried to put together all the evidence we can think of from this now population of hundreds of close-in planets we know about and see how each of these ideas checks out. And we made this giant table that I'm certainly not going to go through in detail. But what I want to highlight is that for different pieces of evidence, we'll talk about just a couple today. There's none of these three channels can explain every piece of evidence. And this leads us to think that we need more than one of these channels, in situ formation, disk migration, and tidal migration, to account for the population of close-in giant planets that we see. And so as I pick and choose a couple of these pieces of evidence to talk about, I'll focus on cases that fit with our theme of how individual system architectures are complementing what we're learning from population demographics. So one big difference between those three different origins idea I described is whether you'd have other planets in the system near the close-in giant. For the high eccentricity tidal migration, which happens after the gas disk stage, this would probably destroy any intervening planets along the way. So you'd end up with a close-in giant planet with no other planets nearby. On the other hand, there's quite likely to be some distant planet or star in the system that is the one that disturbed the orbit, but nothing nearby. Meanwhile, with in-situ formation and disk migration, you may very well have other planets coming along or forming afterwards to be near your close-in giant planet. So complementary lines of evidence are showing us that there's probably multiple channels at work. From population demographics, particularly from the Kepler mission, which was sensitive to even very low mass nearby planets, we learned that most hot Jupiters lack nearby companions. And this is consistent with what we'd expect from the high eccentricity tidal migration channel. But there are exceptional systems like WASP 47b, which is a close-in hot Jupiter with two little nearby planets. And this system is best explained by disk migration or in-situ formation. This is one piece of evidence to tell us that there's multiple origins channels probably contributing. So we usually don't see nearby companions. We're just starting to learn about what kind of distant companions might be in the system and whether they're suitable for leading to this high eccentricity migration. There's been a lot of work done on this, so I'll just highlight one result today. And I'll also bridge to, we have the same questions for these close-in hot Neptunes. So the demographics are showing us that for these hot Neptunes, they also seem to not have nearby companions. So on the left is a result from Dong et al. Showing that planets between about 2 to 6 Earth radii, so close-in Neptunes, tend to be singles detected in their system in blue, in contrast to smaller planets. So they seem to be similar. Hot Neptune seem to be similar to the hot Jupiters that way. Complementary to that, we're starting to learn more about the distant companions from the Gaia mission and the astrometry there. So there's a close-in hot Neptune in the Pi Mensae system, and I worked with Rob DeRosa, who used Gaia astrometry to measure, are those two planets in the same plane as each other, and found that they are not. They're in very different planes. And when we simulate the system's history, that outer inclined planet is very consistent with causing a perturbation, and then high eccentricity migration can take over for the inner planet and lead to this close-in Neptune that's in a very different plane from its distant outer planet. So as we try to make headway on this debate and learn about these different origins channels, another really important property to look at is the eccentricity of the planet. So this now is a cartoon of eccentricity versus semi-major axis. Earth is at 1 astronomical unit. We call a hot Jupiter something that's within 0.1 astronomical units. And this plot is showing how different physical processes populate this parameter space. For example, planet-disk interactions at the bottom can move a planet around, but tend to keep the eccentricity of the planet pretty low. Scattering close encounters between planets can lead to highly elliptical orbits further from the star, but when you get very close to the star, that's less effective. And the high eccentricity tidal migration channel in red brings things from a very elliptical orbit to very close to the star. And you can see that there's part of this parameter space that's only red. So things that are close to the star at a pretty high eccentricity can't be easily explained by anything but high eccentricity migration. In the observed population now of giant planets, there are indeed giant planets in this part of parameter space. And the best explanation for these planets is that they started on more elliptical orbits and are in the process of tidally circularizing. Another piece of evidence that supports that is when we look at the ages of their host star. So now we're zooming in to within 0.1 astronomical units, and we're color coding giant planets by their age. And we see that planets orbiting the younger stars in blue are systematically at closer periapses than the older stars, suggesting that they're tidally circularizing over time, and that at least some of the circular planets we see on this plot used to be eccentric and have tidally circularized. So a question we have now is, okay, there's good evidence for tidal migration for these hot Jupiters, that there's some other channel as well contributing in situ formation or disk migration. But what about the warm Jupiters between 0.1 and 1 astronomical units? We have the same question about whether these warm Jupiters, which are still closer to the star than we traditionally thought a giant planet would have formed, what kind of origins channels are they coming through? Is it the same mix? Is it one or the other? And they have the same possibilities that maybe they formed closer in than we expected. Maybe they disk migrated there, or maybe they're in the midst of high eccentricity tidal migration. One challenge that we face with this last explanation is that there doesn't really seem to be many eccentric planets in this part of the plot, these warm Jupiters. And we found a while back from the Kepler mission that there's actually a significant absence of planets in this part of parameter space. So warm Jupiters on very eccentric orbits compared to what we'd expect if these close-in eccentric Jupiters went along this whole path and tidally circularized. So this has been something that we've been puzzling over for a while. And recently I think I'm starting to understand things from a little different perspective, from looking at some individual systems where, again, the detailed characterization of an individual system is going to complement what we learned from population-wide demographics. So I'm going to talk about 3 different systems that have been helpful for this. One called TOI 3362b is what I'm calling a warm proto-hot Jupiter. So it's a warm Jupiter that seems like it's on its way to becoming a hot Jupiter. The next is Kepler 419, which is a failed hot Jupiter. Seems to be a planet that missed the boat on becoming a hot Jupiter and is going to be stuck as a warm Jupiter. And then I'll finally talk about a pair of resonant warm Jupiters in the TOI 216 system. Okay, so I mentioned how we were missing the expected number of these Jupiters on very elliptical orbits out in the warm Jupiter region. The box I labeled missing, but TOI 3362b, which we found and characterized with the TESS mission, is in an intermediate part of this high eccentricity migration track between the eccentric hot Jupiters that we know about in abundance and the missing eccentric Jupiters that we ruled out from the Kepler mission. So it's still quite close to its star. It's at 0.2 astronomical units, but it has quite a high eccentricity of 0.8. So it seems like it's well on its way to becoming a hot Jupiter. So I'll go back to what this might be telling us in a moment, but I next want to talk about another piece of the puzzle, which is Kepler 419b, the failed hot Jupiter. So this is a planet that also has an eccentricity of about 0.8, but it's out on a 70-day orbital period, and it's not eccentric enough to be getting close enough to the star for tidal circularization, we think. It's accompanied by a number of such planets in that part of the parameter space. But one thing that we had to rule out is that one explanation for planets like Kepler 419b is that maybe there's another planet in the system that's periodically disturbing them to a higher eccentricity so that they can be kind of sporadically migrating and circularizing. In the case of Kepler 419b, we were able to rule that out using a powerful technique of transit timing variations. So this might be quite familiar to the audience, but just in case it isn't, when you have a planet in a system all by itself, it's going to transit very periodically. But if there's another planet in the system gravitationally disturbing it, that can cause variations in the transit time. So the movie's going to now zoom out and show a multi-planet system. So now we have another planet disturbing our transiting planet, and now the transit times aren't periodic. And with good measurements in a large number of these transit times, we can often characterize the system in great detail, like much better than any other technique. And in this case, we could constrain there is a non-transiting planet, what its orbit is, the full 3 dimensions of it. We can simulate the system over longer timescales to see, does our inner planet ever get eccentric enough to tidally circularize? And we found that it doesn't. Now we know all about that other planet, and it's not an explanation. This planet still never gets eccentric enough to tidally circularize. And we even explored what if there's other planets in the system that we don't even know about, and except a very special part of parameter space, they wouldn't really be able to contribute as well. So this planet is stuck here on this elliptical orbit that's just not elliptical enough to be tidally circularizing. And because of that, we don't think it originated from further out to circularize here. This is kind of where it's been. So we've recently been thinking that maybe high eccentricity migration happens, but it starts closer in than we thought, not out where our own Jupiter is, but fairly close to the star following in-situ formation and disk migration. That's one explanation for why the planets further back are missing, why we have these failed hot Jupiters that never got eccentric enough to tidally circularize, and why we are starting to detect planets that are at, say, about a fraction of an astronomical unit that are in the midst of tidal circularization. So if that's the case, which is it, in situ formation or disk migration? How can we better understand the process and systems where we get a planet close to the star through one of those channels? So the TOI 216 system has been really helpful for that. This is another test discovery. And it's part of a collection of warm Jupiters. So I made this cartoon of all the warm Jupiters at the time. This is every warm or hot Jupiter that has another detected planet in the system. So you can see that WASP 47 hot Jupiter that I mentioned at the top. Most of the other planets on the plot are warm Jupiters, so they have periods between 10 and 100 days. And you can see that many of them happen to be near integer period ratios, which tells us something at least about their origin. So when we see an integer period ratio, we often think, well, maybe it's in or near an orbital resonance. An orbital resonance, we are very familiar with from different systems in the solar system. One example are Io, Ganymede, and Europa orbiting Jupiter, which have a 4:2:1 integer period ratio. And we often think if we see an integer period ratio and a mean motion resonance is what it's called, that some sort of dissipative process was at work, putting the system into that configuration, maybe disk migration, maybe tidal interactions, maybe planet disk interactions. But just having a near integer period ratio is not officially in resonance. To be officially in resonance, you have to look at the resonant arguments, which involve a combination of the position of the planets and their periaps in a system, a three-body resonance, as we would call it, like this example. Then we'd have a combination of positions of all three of them. And we have to see this angle librating, which means it does little oscillations around a single value instead of sweeping through every possible value for it to be officially in resonance. So it'd be helpful to know if these systems are in resonance. That would tell us something, we would hope, about the process that got them there. But for most of these systems, we just don't have detailed orbital characterization to tell us if the system's actually in resonance or just near resonance. In other words, we can't measure and simulate that angle over a long term to see if it's sticking at one value or sweeping through every value. So usually the resonant behavior is uncertain. So why are we interested in it? What could be the origin of these close-in giants to get them here? There's still debate about, just like as I've been talking about for a while, about how these close-in giant planets got here. One possibility for these resonant warm Jupiters is that they form much further out and migrated in through the disk, and that's what captured them into orbital resonance. So this was an explanation for GJ876, which is a planet on here. And this is actually a case where we do know that the resonant argument is librating. That system has been characterized quite thoroughly. But you don't necessarily need a large-scale migration to get captured into resonance. For example, we've been exploring how giant planets can get captured into resonance just by interacting with each other and their local gas disk without migrating very much. And we've been exploring how in situ formation, which I'll talk a little bit more about later, can also get things into resonance. So when we talk about if something's in resonance or not, what I want you to focus on is that resonant argument, that combination of angles that I talked about with Io, Ganymede, and Europa, and that's circled with red on my slides. When you see that sticking at one value with little oscillations, that means it's in resonance. So the ones I circled are examples of that angle where the system does end up in resonance without undergoing long-scale migration. So let's get back to TOI 216 system. The method that I mentioned earlier in the talk, where we see a planet transiting non-periodically, helps us characterize this system in great detail as well. So these are plots of the observed minus predicted, where predicted is if it were perfectly periodic, for the two planets in the system. And you can see that the transit times are swinging wildly by hundreds to thousands of minutes, which is quite dramatic for a transit timing variation. So these two planets are very strongly gravitationally disturbing each other. One challenge with these transit timing variation measurements that we now have for a number of systems is that there's often a degeneracy when you try to characterize the system between mass and eccentricity. So you can see some orbital probability distributions here, where just for now, look at the blue one, you can see that there's, with just the first year of test data, a strong degeneracy between the eccentricity of the inner planet and the mass of the outer planet. And that translates to a lot of uncertainty in the resonant behavior as well. With this system, though, we are able to bring in a lot more data to help us learn more. So we got a bunch more transits for this system, seeing the planet pass in front of its star from ground-based telescopes and from the TESS extended mission. And also just the third year of the TESS mission, which revisited some of these fields. And several radial velocity teams characterize the system using the reflex motion of the host star, which is another very prolific way for characterizing planetary systems. So putting all of this together helped us break that degeneracy. And in particular, you can see the black probability distribution. This is what we're learning from the radial velocity measurements. They're not so sensitive to the eccentricity here, but they're very nicely constraining the planet's mass. And even the extended baseline alone of just having more and more of those transit measurements, which you can see in red, really also narrow down the parameter space. So when we put all of these things together, we get a system that's characterized in excruciating detail. I'm now plotting on the left the eccentricity versus semi-major axis, where the little clouds of blue and red points are like the final fit with all the data set. You can see we've really honed in on what all the orbital elements are. And this is going to let us really understand the resonant behavior a lot better. So let me tell you what we found about the system that was a bit surprising. So for understanding that resonant behavior, is mentioned how that angle needs to be oscillating around one value with a small amplitude. For this system, it is oscillating around one value, but it has a fairly big amplitude. You can see that on the plot on the right. The right is eccentricity times sine and cosine of that resonant angle. The fact that this little bean is not passing through zero tells us it's in resonance, but it's doing a pretty big libration, and its libration amplitude is very tightly constrained, 60 plus or minus 2 degrees. So this is a system where it's in resonance, but it's not super, super tightly in resonance. And this is a bit different from what we expect with a lot of the simulations where it's just driven there by disk migration. It also has what we call a free eccentricity. This is the eccentricity of the planet that's not being caused by the resonance. It's kind of like an extra eccentricity. And so that's small and significant. And there's even a small but significant mutual inclination between the planets in the system. It's just a couple degrees, but that's actually quite different from the ultra flat systems that we often see in the exoplanet sample. So this is a system where it seems kind of quiet. There's like two giant planets. They're not ultra eccentric. They're close to the star, but there's a bit of a sign of disturbance with this libration amplitude and free eccentricity and mutual inclination. So we've been exploring different scenarios that could help explain this. Here we see some simulations of a possible orbital evolution. And on the top, that's one of those resonant angles where in red is the observed that we're trying to match. So we're trying to get like a fairly big amplitude. And there's a number of ways that this could be done. One is by having some other body in the system kick the planets either before they get captured into resonance or after. We could have a crossing of the orbital resonance with disk precession that might also help us explain the mutual inclination between the planets. And then there's a recent paper exploring how dispersal of the disk or turbulence in the disk could help shake things up a bit as well. So this is kind of the opposite of the other two cases I talked about. With the other two cases, I was saying, well, maybe they migrated in or formed there and then had this strong disturbance that led to high eccentricity tidal migration. This would be like a very gentle case where they maybe formed in situ or migrated and then had a little bit of a kick, not enough to lead to high eccentricity migration, but enough that it's affected the orbits and it's not the simple smooth disk migration that we often naively start with. So to summarize this part of the talk, there's strong evidence for at least 2 origins channels for hot Jupiters, one of which is high eccentricity tidal migration, and one of which is in situ formation or disk migration. From the current evidence, it's a little hard to tell the difference between those two. And then I showed some tentative evidence that high eccentricity migration might be preceded by disk migration or in situ formation. So we have kind of all of them operating in one system, and that there may be disturbances that follow disk migration or in situ formation that sometimes lead to an extreme outcome and sometimes are more of a little jostle. And that may be a difference in disk conditions that establish these different pathways. So I will pause for a moment before going on to the second part of the talk to see if there's any questions about this part.
I'll jump in with a quick question.
Yeah.
So can you talk a little bit about the relative eccentricity versus inclination in this previous system in terms of, right, is this close to equipartition between the two? Is it evidence that there is stronger pumping of the inclination compared to the eccentricity? I don't have a good sense for what I should be expecting.
I think it's actually pretty similar order of magnitude with the eccentricity and inclination. Okay. So even though this resonance crossing, this is like a inclination resonance that could actually, I think, happen without even disturbing the eccentricity. That's kind of like a special inclination exciting thing. I mean, that could happen, but I think the nice thing about just kicking the planet is that could excite either eccentricity or inclination kind of equally. So yeah, it's kind of equally, very roughly divided in both.
Okay.
And the hope is that we might actually be able to even better pin down this mutual inclination by seeing basically the chord the planet transits across gradually change with even more transits that are being observed.
And then just a related question in terms of, if the mutual inclination for this system was representative of these, warm systems, what does that say about the rate at which we've observed these multi-planet systems, given the, I guess, lower probability of transits for high inclination? Or not high inclination is the wrong word. But.
Yeah, so this is actually pretty different from the bulk of the Kepler test population, the super Earths and mini Neptunes. For those ones, there aren't as many systems where we can do this kind of detailed analysis, but there's a lot more population demographics, and things need to be pretty flat in order to get the large number of multi-transiting systems. So even though this seems like kind of a small mutual inclination. This is big compared to like the super quiet Kepler system, like super Earth mini Neptune systems. But there aren't that many like two giant planet systems from either Kepler or TESS. So it could be typical of systems with multiple close and giant planets. We don't have enough of a sample to divide it out. Interestingly, though, there is like a pair of planets that they both transit, but they have like a 30-40 degree mutual inclination. And that implies that there's probably a bunch more where we only saw one of them transit, because they kind of had to be like going at this angle for us to both see both of them transit. That was work by Mills et al., I think 2016 or something. So yeah, I think this is just further sign that we see very different behavior and architectures with the giant planet systems versus the systems that only have smaller planets.
Well, I guess I was thinking about the giant planet systems. Like if this was typical, then it would be consistent that you don't see very many dual transiting giant systems.
Yeah, because even with this one, I mean, that other one is like so weird, but this one, one of them is like barely transiting. So yeah, as you say, there's probably other ones like this where we only see one of this planets transiting. That being said, it does have really strong transit timing variations. So it is a case where if we'd only seen one of them, we would have at least known there's something else there from the transit timing variations.
Right. I guess so. That's the question is, can you rule out this being common just based on the lack of TTVs in a lot of these other systems? Like they've all been searched, obviously.
Yeah. I think that is a good question. I haven't, and I'm not aware of like tried to reconcile those two things, because having this one and that other system I mentioned implies that there's a lot of others, but I part of it is there's just not even a lot of transiting warm Jupiters, but there's also not a lot where we see strong transit timing variations either. And though when there are strong transit timing variations, it's like everyone jumps on that system because it's a giant planet. It's like, woohoo, it's Christmas in a present stocking. So it's not like there's a bunch of them that are just sitting on the table to be looked at. So that your question is making me wonder if that's all consistent, and I haven't seen that looked at. I would be interested to know the answer too.
I think Renu has a question as well.
Yeah, Becky, I'd like to poke a little bit more at the system you were just talking about. I see that the masses of these two planets you homed in on are actually very similar. They're almost equal. If you go back to the slide you were just showing us. The next one, I think. Yeah.
I don't actually have the this is my plot being misleading, I'm afraid. I don't have the mass of planet B on there, and it's actually it's a Neptune. It's only, I forget if it's 20%. It's a lot smaller than the other one. So
isn't that the red one on this plot?
So that's the yeah, I apologize. It's confusing the way I have it on the plot. That's the eccentricity of B, but not the mass of B. So it's only the mass of C is being plotted here.
Oh,
and
I see. Okay, so
the reason I'm doing that in that weird way is because that's where the degeneracy was, between the eccentricity of B and the mass of C. But I'm not plotting mass of C since that didn't have that degeneracy, but it is significantly smaller. So it's an outer. I'm like doubting myself if I remember which one's outer and which one's inner. Let me go back to my picture of them.
well, the resonant angle you're plotting would suggest that B is the inner one.
B is the less massive one. Yeah. Oh, yeah. And you're right. The resonant angle. Yeah. So I think you're right. Yeah, the inner one is less massive, and yes.
I see. So those red points in the left panel here would be displaced. I guess the mass scale is not the same for the red points and the blue points. Okay. All right.
That's
Now,
correct.
the other question I had was, you talk about this forced and free eccentricity. Could you expand on that? What do you mean by forced? I mean, basically at any resonance, you can have a whole range of eccentricities that are stable points.
Yeah, okay, so that's a good point. So the way I calculated this was where the like that to like approximate the free and forced making a vector sum, the what I'm calling the forced is like the average, and the free is the amplitude that's oscillating around that, which I know is not a perfect way to describe it when both planets have a mass. There's also a definition that relates to the transit timing variation analysis where what's called the free eccentricity there is what's leading to, is like what's driving up the transit timing variations. So that's how I was picturing it, but I do see what you mean, that there's like a lot of possible eccentricities associated with the resonance. So let me ponder that further and get back to you.
Yeah, because in that, the way I think of it, there should actually not be any correlation between the forced eccentricity and the mass. So this must be some kind of data analysis issue more than physics issue.
Yeah, so there isn't, except that observationally we know what I think it's more of a, I think the correlation in what's affecting the transit timing signal is between the free eccentricity and the mass, as you say, not the forced eccentricity and the mass. And I think if I could make this plot with free and forced, we'd see really strong with this should be free, but what I'm getting out of the fit that I do to the data is just the total eccentricity.
I see. Okay.
And to get the free and force, or what I'm calling the free and force, I actually have to like simulate it for a long time and then do that average and then amplitude of variation.
Okay, we should probably talk about it offline, but is there any significance to the fact that the best fit, I think that's what you mean by these dense blue points and the dense red points, that say the blue points, that they show up at some kind of minimum of your possible fits?
Yeah, that's a good question. I see what you mean, and I haven't thought about it. Let me think about that and get back to you. It seems like you're right. That does raise that question. Yeah, let me think about it and get back to you. Thank you.
Okay, thanks.
Okay. So I will now go on to the second part, and I'll keep it brief because I think I have maybe 5 to 10 more minutes ish. So the second part is about compact multi-planet systems. Kepler 11 is kind of a poster child where we have a bunch of close-in planets all packed within the orbital distance of Mercury from the sun. And from ground-based radial velocity surveys and transit surveys, space and ground, learned that planets with orbital periods shorter than Mercury and sizes between Earth and Neptune's, which I'll call super Earths in this part of the talk, are commonly detected. We can see that on this plot of detections. There's a lot of them in that part of that have been detected by the Kepler mission here. And the colored points are systems where more than one planet in the system transits and is detected. People have done a lot of work then taking these detections and using it to calculate occurrence rates. And they found that these planets interior to Mercury's orbit, sizes between Earth and Neptune are also intrinsically very common, and that many reside in compact multi-planet systems. So we have a lot of the same questions about their origins as we do about the close and giant planets. Did they form there? Did they migrate there? A compact multi-planet system probably didn't undergo tidal migration, but the other two origins are a possibility. So in particular, there's a lot of debate on whether they formed in situ or came in through disk migration. In these cartoons I'm showing, we have a gas disk in green that's going away over time. And then we have in left, I'm showing an in situ formation scenario where we start with planetary lunar Mars mass embryos that, as the gas disk starts to go away, can grow through giant impacts, accrete a tiny amount of gas, and become a super Earth or mini Neptune, similar to the process through which our own terrestrial planets formed after the gaseous stage. Or we can have these super Earths and mini Neptunes form much further out in the disk and migrate in. So how can we tell the difference between these two scenarios? Well, an original thought was that maybe orbital resonances could distinguish. Since orbital resonances imply some dissipated process at work, the thought was that maybe this disk migration scenario would give us resonances and the in situ formation scenario wouldn't. So we need to go out and see how many of these systems are in resonance. This is another case where what we're learning from individual system architectures is really complementing the population demographics. So on the population demographic side on the left, this is a histogram of adjacent period ratios between planets, and orbital resonances, integer period ratios are marked. And there's not a huge pileup at any of these resonances. So there's not like the majority of these systems with integer period ratios. But there are some special systems that do have orbital resonances and that even have a chain of planets and integer period ratios, like the TRAPPIST system or the Kepler 223 system. So now we have to try to make sense of this. One thought people had is that maybe you could either break the resonance or avoid capturing, so that maybe disk migration wouldn't always lead to resonances. Another possibility is that we could get these resonances just by forming the planets close to their location. And so we need to come up with something that gives us, in general, things aren't in resonance, but there are some special cases where they are. So we've been investigating this in situ formation scenario. And one of the first things we did was to look at some of these individual systems and simulate possible orbital histories for them. So this is showing, again, the top plots are like these resonant angles that we want those to be really tight if they get captured into resonance. We have the TRAPPIST-1 system, for example, and we have a scenario where they migrate a long distance from their formation location, where they just migrate a tiny bit, and where they don't migrate at all, but they interact with the gas disk and that affects their eccentricities. In all three of these cases, we can get that angle nice and tight captured into orbital resonance. And that's true for the other known resonant chain systems that we looked at. So so this can happen. This is like we took the planets as we know them, we migrated or damped them. We get resonances even without migrating them very much. So that's nice to know, but how often does it happen naturally that we have things just forming in situ and they get into a resonance? So I'm now going to introduce, we have a suite of simulations that we're going to use to look at a few different properties. These simulations start with embryos whose initial conditions are set by the amount and distribution of solid material in the disk. We have a gas stage where we have forces that are damping, like simulating the effects of the gas disk. And then we have gas accretion that's painted on after the fact. And then we have a post-gas stage where we evolve the system for much longer, though usually not much changes too dramatically after the gaseous stage. So I like to think of these simulations as somewhere between the long list of ingredients ravioli and the store-bought package ravioli. So we find with these in situ formation simulations that we sometimes do make systems with resonant chains. For example, our simulations, we just looked through them all and we found systems that had resonant chains, including one with a chain of 6 planets, kind of like that TRAPPIST system. And the rate of us making resonant planets was about similar to what's observed, with the caveat that the observed is very small number statistics. We can also make that wide range of orbital period ratios. Here I'm comparing the observed and simulated, and where it's overall, it's a wide range, and then there's a few special systems that are in resonance. So I think we can now put a question mark here as well and say that in situ formation doesn't necessarily imply no resonances. So I'll now ask, let me just spend a couple minutes on this. Can the in situ formation scenario account for other important properties? And this is, again, a case where we want to draw on both individual systems and population demographics. So interestingly, in these systems of super Earths and mini Neptunes, we see a lot of variation in the mass radius relation. So on the left, this is showing radius versus mass. And this statistical study found that there's a lot of intrinsic scatter there. So a planet of a given mass in one system, it has this size, and another it has that size. For looking at individual architectures of these systems, people have found that even though there's a wide range overall, like different sizes, different spacings, within each system, it's somewhat self-similar. This is called the peas in a pod trend. So each system has kind of similar sizes and spacings for its planets. One explanation for this is different in situ formation conditions. When we have more solids in the inner disk, we can grow the planets while there's still some gas around. They can overcome the gas damping, and this can lead to more compact systems that are more likely to have low mass gas envelopes and be puffier. Meanwhile, in disks with fewer solids in the inner disk, we have to wait around for the gas to go away since we have fewer solids and grow the planets then. And this leads to rockier planets and wider spacings, more inclined in elliptical orbits. And this idea is interesting in that it links planets' compositions to their orbital properties. So I'm now showing on the left, in our simulations, this is now all simulations, we're making a lot of scatter in that mass radius relation, where the sizes of a planet at a given mass is also connected to their orbital period ratio. So the more compact systems have puffier planets. On the right, I'm showing how, even though there's a lot of diversity overall, within each similar simulated system, there's similar sizes and period ratios for the planets. And here in our simulations, that underlying parameter that's controlling this is how many solids we have around in the inner disk. So to briefly summarize, compact multi-planet systems, these planets may have formed close to their stars without significant migration, even the resonant ones, though the jury's still out on whether that's definitely the case. And different disk conditions may lead to their diversity of orbits and compositions. I'm going to skip this very brief part about wide separation planets and super briefly touch on right now, we have this very fragmented view of planetary systems because of the different detection techniques, and that future missions and surveys will both expand our parameter space and give us more dimensions on each known system. We can try to put things together like we do in the solar system to get a full story of each system, where I've envisioned what that might look like on a pretend planetary system where we have all these different measurements of orbits of the planets, atmospheres, debris that we can put together into a coherent story. So I hope I've showed that what we're learning from individual system architectures can complement what we learn from population demographics. And I'll leave you with this summary. Thank you so much.
All right, I'll clap for everyone who doesn't unmute. Thank you. This was really, really fascinating. I know we had some interruptions in the middle, but are there other questions? I see 2 hands clapping so far on the participant list, but I'll just wait a second. Or feel free to unmute yourself to ask questions. All right, I think we may have gotten most of the questions out during the talk. I don't think, I imagine Rainu and I could go back and ask you a few more questions about the TTV systems, but maybe that is better for offline. I see a thumbs up from Rainu. Okay. All right. Well, if you don't want to jump in, then Rainu, then I guess I will just conclude, or maybe if you want to hang out for 2 minutes, if others want to listen into that, you can. But thank you all for coming, and we will hopefully see many of you in person at a TAP Talk in March.
Yeah, thanks everyone.
Thanks, Rebekah.
So if you're actually, can I ask you one other demographics question? I think the answer is probably this isn't something you've looked at either. I mean, do you happen to know what the relative occurrence rate is of companions to warm Jupiters as compared to the overall multiplicity, accounting for all of the various, selection biases?
Yeah, so they very commonly have other nearby planets in the system. It's very different from hot Jupiters that way. And they also commonly have like an outer giant planet. I won't say it's in the same system because it's the nearby small planet thing comes from transits, and then the more distant giant comes from radial velocities. It's 2 different sets of systems, so we don't know how much, whether it's literally the same systems or not, but both types are quite common for the warm Jupiters, and that's quite a contrast from the hot Jupiters, which don't have other ones nearby, but they do very commonly have outer giant planets in the system.
But what about compared to just your run-of-the-mill super Earth?
Yeah. Oh, that's a good question. I don't know that we've pinned that down very well. I think we know it's common for super Earths to have other planets in the system, though there's still some unresolved degeneracy between mutual inclinations and it being intrinsically single on their own.
Sure.
But I think what we can say is that in both cases it's common, but I don't know that we can, if we know enough to compare them and see, is it more common to have a companion if you're a warm Jupiter or a warm super Earth?
Okay.
That's a good question. I
because
haven't seen that.
Yeah, there's been some work recently on, do you promote or prohibit the formation of giants by, do you promote the formation of super Earths or smaller planets by having a giant in the system or not?
Yeah, and there's also very commonly a giant planet at a few AU has super Earths
Right.
inside.
Yes.
And I saw a very recent paper that found like a slightly lower rate than some of the earlier studies,
Yeah.
but it's still extremely common to have that configuration as well. So that's still an area I think that I'm wondering about. Is it like, are the warm Jupiters the tip of the super Earth multi-iceberg, or the tip of the hot Jupiters the tip of the warm Jupiter iceberg? Like, how do all these fit together? Or are they all just quite different in terms of the relative contributions of different origins channels?
Mhm.
Yeah,
I-
so those are great questions.
I'll let Rainu go ahead. I'm sorry for dominating.
No, that's fine. There are many questions I have, Becky, and maybe we'll get a chance to discuss them some other time. I'll just ping you sometime and we can find a time to talk. But
that'd be
I
great.
was, if you can quickly, maybe this is a quickish question on the high eccentricity migration. What is being envisioned as the, how do you form something in high eccentricity at a large orbit?
Yeah, so there's still a lot of there's been like a number of different scenarios proposed there, and still a lot of debate about which it is. So you can have like planet scattering, like you start out with very closely packed planets and they scatter each other. You can have secular interactions, either coplanar secular or Kozai leadoff mutual inclination, or you can have secular chaos like in the solar system, exciting eccentricities that way. And I think the big challenge is that none of these are really quite efficient enough to produce the ratio of hot Jupiters to cold Jupiters that we see. But all of them are a potential explanation, and I think better characterization of the outer system can at least somewhat distinguish, like, okay, are the outer planets on the same plane or not, and help tease that out a little bit.
I see. So basically,
or it could be another star too in the system, but the reason that I favor a planet explanation was a reason I didn't show, but these eccentric Jupiters that I said are on the path to tidal migration tend to be orbiting the more metal-rich stars, in contrast to overall hot Jupiters, which, I mean, actually they all are metal-rich, but there's a combination of metal poor and metal-rich for hot Jupiters as a whole. So that seems most consistent with another planet doing it, but there certainly may be systems where it's actually a binary star causing the perturbation.
I see. Okay, so some kind of orbital dynamical instabilities in a mature multi-planet system or a third body of an external or companion star. Okay, I see.
Yeah, that's generally what people are thinking. And I've also seen some cases where like a resonance is crossed during a disk dispersal or something like that to generate the eccentricity as well.
Okay. Thanks a lot.
Yeah, thanks so much, Renu.